Hello Hamza, how are you?
Fine, sir.
Okay, very good. So, we were discussing the Kirchhoff's law. Okay, we were discussing the Kirchhoff's law, and we have completed one question based on Kirchhoff's law. And I am hoping that you have got that question. This was the question, and I think we have completed all parts. And now I will discuss this question. First, read the question. And this is the question already appeared in your board exam. So just read it once and then, okay. So they are saying drive an expression for the internal resistance of a cell in terms of EMF and terminal potential difference of cell. So what you will do in this question, you will take a cell and you will connect this cell with an external resistance. Okay, this is the external resistance, this is the internal resistance R, this is the EMF, and current is flowing in this direction. Current is flowing in this direction, and we have to drive this expression. V is equal to E minus IR. I have told you, when I have written this, I have told you that I am not driving the equation that time. I have told you, and I have also told you that we will drive this equation using the Kirchhoff law. So this equation can be derived using the Kirchhoff. So see how this equation we will get. So the current is this, and for applying the Kirchhoff's law, we should have a loop, and in that loop we will apply the Kirchhoff law, and we will follow a certain path also. So I am supposing a point A, this is a point B, this is a point C, and this is a point D. So you can choose any path. So Hamza, tell me which path do you want to choose? A, B, C, D, C, D, A, B,
ABCD.
A, B, C, D. Okay. So simple path A, B, C, D. You have chosen in the loop, and the direction of current is this.
ABCD is the direction of the current.
Yeah. Huh. Yeah. Means you have choose a path in the direction of the current. And what is the potential drop across this R? IR, V is equal to IR is the potential drop here. And what is the potential drop here? Here is the potential drop IR. If talking, okay.
Yes,
If
sir.
talking about the magnitude only. So where you will apply the Kirchhoff's law from in this loop A, B, C, D, then you will apply. So you will write I into R. Okay, IR, and you will take this as negative IR because you are moving in the direction of current. So now from here to here to here, here is another potential drop. This also you will take minus IR, and this you will take plus or minus.
We'll
From
take
here,
minus.
no, we will take it plus because we are moving from lower potential to higher potential. We are moving from lower potential to higher potential. Okay, Hamza, are you getting my point?
Sir, your voice is stopping between. Voice
Means
is cracking.
my voice is cracking.
Yes.
Actually, there is a power cut, and so that is why I have connected with my phone. My Wi-Fi is not working now, so that is why. Okay, should I start? Okay, no, it's fine. Hamza, now it's fine.
Yes, sir.
Okay, just see here. So this E you will take as negative or positive because you are moving from C to D. So you will take this E as positive, and this is equal to 0. So you can write this equation as this minus IR is equal to this minus E plus IR. You can write this equation like this. Okay. And when you will take minus common from the both side, you will get IR is equal to E minus IR. And what is this IR? This IR is the potential drop across this external resistance. So this is V is equal to E minus IR. Okay. So this V, what is this V? This V is actually the terminal potential across this cell. Okay, terminal potential. So in this way you can drive. Terminal potential difference. Okay. So with the help of Kirchhoff's law, you can drive this. So this is your final result. Okay, just please take the screenshot and just zooming it out. And after that, we will solve next question. And when okay, take the screenshot, please. Taken, Hamza?
1 minute.
Okay, fine, no problem. You can take your time.
Done.
Okay, very good. So completed. Okay, na? So I am just now. This is the next topic. You can say this is the next question that we have to solve. So this is the topic. You can write the heading equivalent resistance using Kirchhoff's law. This is very simple that In this, I will use that R equivalent is equal to E equivalent divided by R equivalent. Oh, sorry, I total. Not equivalent. You can write this total voltage R equivalent is equal to total voltage divided by the total current. We have already discussed this. There is nothing new in this. Okay. So this, with the help of this, we will calculate the equivalent resistance of this type of circuit. So you can see here a square is given, and at each edge of the square there is a resistance. So we have to calculate the equivalent resistance across diagonally opposite ends. Diagonally opposite ends. Diagonally opposite ends means you have to calculate the equivalent resistance between the point G or A. These are the diagonally opposite ends, or between E and C. These are also diagonally opposite points. F and D. Okay. So you have to find. So how many resistances are there? Can you tell me how the total number of resistances there in this? Can you count the number of resistances?
Yes, sir. 4 plus 4, that is 8, 9, 10, 11, 12.
Yeah, means we have 12 resistances connected like this, and we don't know what kind of combination it is. Okay. So what we will do, if we do not know about the combination, we will apply the KVL. Simply we will apply KVL. So here I will apply KVL. So we have to find the potential difference across this point A point and this G point. Okay. Just connect a battery here. Just wait. Okay, connect the battery here like this. So it means that you have to calculate the equivalent resistance between diagonally opposite points. These are diagonally opposite points A and D. If you join A and D, you will get a diagonal of this cube. Okay. So now suppose the EMF of this cell you have connected is E, and current is flowing here in this direction like this, and I is the current flowing. Okay, I is the current flowing. So what you will do now, here I current is flowing, and this A point is the junction point, and from this A point there are three branches emerging. One branch is this AE, another branch is AD, and another branch is AB. So this current will be divided equally across the three branches. So in this branch, the current will be, can you tell me what is the value of current? Hello, Nida. Hello, Nida.
Hi,
How are you?
I'm good, Alhamdulillah.
So you are in this batch?
Yes,
Okay, fine. So we are discussing the Kirchhoff laws. So have you completed the Kirchhoff law?
yes,
Okay. So I am telling you that I am discussing this question, and after this question, I will discuss the next topic. Then you will get it. Okay, easily. So you can see here, this is the circuit given. Okay. This is a circuit given, and we have to calculate the equivalent resistance between this point G and between point A. Okay, so what I have done, I have just connected a cell between this point G and between point A. Okay.
Yes.
Yeah. So you have to keep patience, and when I will discuss the next topic, then you will get from the starting. Okay. So you can. This is very simple question. So suppose the current is I. Current I is flowing like this. Current I is flowing like this. So this A point is the junction point of three branches. From A point, there are three branches emerging. One branch is this AD branch, another is AE branch, and another is AB branch. Okay, so this current I will be equally divided across all the branches because the resistances in all the branches is same. The current will be divided equally. So how many branches we have? Three branches, and we have to divide the current equally in three branches. So the current will be divided like I by 3. Means in this branch the current will be I by 3. In this branch the current will be I by 3. And here the current also will be I by 3. Okay. So now Hamza or and Nida, when you will move from A to D, this current will continue flow. This I by 3 will be here. Means in the branch, if you are focusing on this branch AD, so in this branch the current will remain same because this is a single wire. Okay, and at this point, this D point is the junction point. Now what will happen? From this point, two branches are emerging. So again this current will be divided equally. Again this current will be divided equally because in this branch and in this branch the resistances are equal. So how you will divide this I by 3 equally into the two branches? This I by 3 you will divide I by 3 by 2. You will get the current I by 6 here. You will get the current I by 6 in this branch in this direction and I by 6 in this branch. Okay. So after that what you will do, you will move through this branch and you will reach at this point E. So I by 3 current here in this branch I by 3. So from here this there are two branches. One branch is this and another branch is this. So similarly the current will divide. Here the current will be I by 6. I divided by 6. Here also the current will be I divided by 6. So now when you will move from A to B in this branch, then you will move at this junction point. Again there are two branches. Then you will divide this I by 3 equally into the branches. Okay. So here the current will be I by 6. Again here the current will be I by 6. Okay. This is the division of current. In the Kirchhoff's law, first we divide the current and then we apply the Kirchhoff's law in the loop. So I have just divided the current now. So now see here, you can just see here, see here. This I by 6 is coming from here and I by 6 is coming from here. So at this junction point, both these current will meet and these both current will becomes, when you will add this I by 6 and I by 6, you will get I by 3. Okay. Because see here the direction of current is this and direction of current is this. When you will add both these current, you will get here the current I by 3 again. And why I am dividing the current, you will get to know when I will apply the Kirchhoff voltage law. Okay, so the current I by 6 is coming from here and I by 6 is coming from here. So in this branch, the current will be I by 3 again. And one thing more, see here, this branch and this branch, I by 6 is coming from here, I by 6 is coming from here. So here the current will be again I by 3. Okay, now suppose you are at point G, you are at point G and you are seeing that I by 3 current is coming from here, I by 3 current coming from here and I by 3 current coming from here. So total current, for the total current you will add all I by 3 and I by 3, you will get the current I here in this wire. Okay, you will get the current I here in this wire. Okay, Nida and Hamza.
Yes.
This circuit is looking complicated, but this is not that complicated. Okay, if you will solve the things step by step, then you will get it. Okay, so why I am dividing this current, you will see when I will apply the KVL. And just have patience. Okay, now we have to just calculate the equivalent resistance between A point and G point. So in KVL, first we have to choose a loop. So I am choosing a loop A. We have to choose a closed loop. Okay, so I am choosing a closed loop A, D, H, G. And suppose this is a point K I am supposing. So I can say I am choosing a loop path in the loop, path in loop A, D, H, G, A, D, H, G, K, A. Okay, K, A. So now see again it. So you have just chosen this path A, D, H, G, and from here from G you are coming through this wire. From here this point K, and again you are at A. Now apply KVL. Apply KVL. KVL means Kirchhoff's voltage law. Okay. So Hamza, can you apply Kirchhoff's voltage law here? From A to D, you are moving in the direction of current. From A to D, you are moving in the direction of current. So you will write minus I by 3 into R. Okay. Because I by 3 into R is the potential drop, and you will take this potential drop as negative because you are moving in the direction of the current. Now from D to H, you have a current this, resistance this. You will multiply both these things, and you will take the negative sign because you are moving in the direction of current. So here you will write as minus I by 6 into R. Okay. And now from H to G, you have current I by 3 into R. So you will take this as negative I by 3 into R. Okay. Now from G to A, when you will come in the path, there is only one voltage, that is E, and you are moving from higher voltage to lower voltage to higher voltage, means you will take this as positive, this E as positive you will take. And according to Kirchhoff's voltage law, the summation of all the voltages in a loop is equal to 0. So these are the summation of all the voltages, and with respect to sign you have to take the voltages. Okay, if you are moving in the direction of current, you will take negative voltage. If you are moving in the direction opposite to that of current, then you will take the positive voltage. Okay, so when you will take the LCM of this, you will get 6 as LCM. Here you will write minus 2 IR. This is a simple calculation you can do. Here you will write IR. Here you will write again 2 IR minus 2 IR, and this is plus E. This is equal to 0. Okay. And here when you will add all these IR minus 2 IR and all that, you will get minus 5 IR divided by 6, and this is equal to minus E. And this minus and minus will cancel out. You will get 5 by 5 R by 6 and E divided by I, means this I you will take in the denominator. And what is this E divided by I? What is this E divided by I? R equivalent. R equivalent is equal to total voltage is equal to total current. And what is the value? 5 R by 6. So R equivalent you will get 5 R by 6. Okay. So this is the another way to solve the question. This is the another way to solve the question. Equivalent resistance if you want to find, then you will write total voltage divided by total current. So this is the total voltage and I is the total current. So E by I is equal to 5 by R. E by I means R equivalent. R equivalent you are getting 5 R by 6. Just note it down. Then we will discuss the new topic. Hamsha, Nida, do you want to note it down or do you want to start writing from the next topic?
On the next topic.
Oh, I am asking from Nida.
From the next topic.
Okay, so Hamza, just take the screenshot. Hamza, you should take the screenshot. No, you are studying from the starting.
Okay, sir.
Why you are leaving this question? This is very good question. Just take the screenshot of this. And you will get this
Done.
question in your exam also. Just take the screenshot of this also. Oh. Taken?
Yes, sir.
Fine. Just take this. Done? Okay. So take this now. So I want to tell you, Nida, that this is the topic Kirchhoff's laws, and chapter number, this is third, and there are two top types of Kirchhoff's laws, KCL and KVL, Kirchhoff's current law and Kirchhoff's voltage law. Okay, so this is we are discussing. So do you have idea about the Kirchhoff's laws, Nida?
Yes.
Okay. Okay. Now we will discuss the derivation of balancing condition of Wheatstone bridge, and this was asked in your examination also. Okay, Wheatstone bridge. Okay. So what is first of all, I want to tell you what is the Wheatstone bridge. Wheatstone bridge is a combination of 5 resistances. Okay, and it is used to find an unknown resistance. Find a unknown resistance. So Wheatstone bridge is like this. Wheatstone bridge is like this. Just keep patience. You will get all the concepts. So okay. So suppose one resistance is here, another resistance is here, another resistance is here, another resistance is here, and this whole combination is connected with some battery or cell. Okay, connected with some battery and or cell. So this time, suppose this is R1 resistance, this is R2 resistance, this is R3, and this is R4. This is R4. Okay, and we have to prove the condition that we have earlier discussed. Okay, and suppose I am connecting one more thing here. Suppose a galvanometer is connected here. G is the resistance of the this galvanometer, and this point, I will suppose this point as A, this point as B, and this point as C, and this point as D point. Okay, so this is the Wheatstone bridge. Okay, and I have told you, if there is no resistance in if there is no current in this galvanometer, or if you have connected a suppose resistor here, if there is no current in that resistance, then this bridge will be balanced. Okay, and the condition will become R1 by R2 is equal to R3 divided by R4. This is the thing. If this thing is followed, if this R1 by R2 is equal to R3 by R4, then you can say there will be no current in the galvanometer. Okay, there will be no current in galvanometer. There will be no current in the galvanometer if this condition is followed. Means you can if you are okay, fine. Now we have to prove this. We have to prove this R1 by R2 is equal to R3 by R4 if there is no current in the galvanometer. This thing we have to prove. Okay, earlier we have write the result. I have not drive this result. So now I am driving this result with the help of Kirchhoff's voltage law. Okay, just see this. See here now. Okay. So the proof, the first thing you will do here, the first thing you will do, you will take the division of current. You will divide the current accordingly. Okay. Okay. So now see here, this is the resistance R1 and I am supposing this by myself. Suppose I1 current is flowing in R1 and what is happening? This is the cell or battery. From here, I current is flowing. From here, I current is flowing. I current is flowing from here to here to here to here. So and here also the current will be I, because the wire is same, the current will remain same. Okay. This wire is same, the current is same. From here, suppose from this is the junction point, this is a junction point. From this point there is one branch this, there is one branch this. Suppose in this branch I1 current is going, so what will be the current in this branch EAD? Can anyone tell me what is the value of the current? Suppose we initially we have I1 current, some current from this I1 goes to this AB. What is the current in AD now? Can anyone tell me? Hamza and uh, Hamza
Yes, sir.
and Nida. Do you have any idea about that? If you don't know, then I will tell you. No problem. You can apply your mind here. Oh, yeah, yeah. You are means the current will be in this direction. Will be good. Current will be I minus I1. Okay, because I1 from this I current I1 is going in this direction and remaining current will be I minus I1 will go in this direction. Okay, so here also the current will be I because the wire is same. So now this is again the junction point. This is again the junction point. So if this is a junction point, so what will happen here? Here at the junction point, the current will be divided. So there are two branches. One branch is this, another branch is this. Suppose I suffix G current is going into the galvanometer. I suffix G current going into the galvanometer. So the remaining amount of current that will go in this branch VC will be I minus IG. Okay, will be I minus. If you are not getting, then Hamza, you can apply the Kirchhoff's current law. Okay, but there is no requirement of this. This is basic maths. So if you have I current and IG goes here, so the remaining amount of current will be I minus I. Okay. So the current here now I minus I. Here also the current will be I minus IG again. Very good. Here the current again I minus I1. Okay. And from here, from this wire, IG current is coming. So here the current is IG. And all these current means this I minus I1 and IG will meet at this point. I minus I1 and IG will meet at this point. So what will be the resultant current? The resultant current you will get by adding both these current. I minus IG, I minus I1 plus IG. So in this direction, the current will be I minus I1 plus IG. Okay, this is simple maths. And same amount of current will flow through this branch DC. Okay. Now we have done the division of current in the circuit. We have done the division of current in the circuit. Now accordingly we will apply the Kirchhoff's voltage law. Kirchhoff's voltage law. So for applying the Kirchhoff's voltage law, first we have to choose a loop. First we have to choose a loop. So you can choose any loop you want. Okay. So I am choosing a loop A, B, D, A. I am choosing this loop A, BDA. Loop ABDA. I have chosen and I will apply Kirchhoff's law. Apply KVL, Kirchhoff voltage law. Now see how I will apply. I'm just copying this diagram here. Okay. Now see, you have to just focus on this loop only. A, B, D, A. Okay. When you are moving from A to B, and one thing more I want to tell you, in KVL, you have to only see the voltages. You have to only see the voltages and you have to add the voltages with respect to the sign of the voltages. Okay. Now you are moving in the direction of the current. You are moving in the direction of the current. And what is the potential drop across this R1? Potential drop means V. V is equal to I into R. This is the potential drop. So when you will multiply this I1 into R1, you will get the potential drop. And sign you will decide whether you are moving in the direction of the current or opposite to the direction of the current. Here you are moving in the direction of the current, and you already know that the direction of the current is direction of decreasing potential. Means here you will take, here the potential is dropping, or you are moving from a higher potential to the lower potential. So it means you will take this minus I1 into R1. Potential drop you will take minus I1 into R1. This I1 R1 is the potential drop, and minus sign you are taking because you are moving in the direction of current. Now when A to B, now come B to D. B to D. From B to D, you will multiply Ig into G, because G is the resistance of the galvanometer, and you will take it with negative sign because you are moving again in the direction of current. Ig into G. Okay. Now from D to A, from D to A, again now this time you are moving in the opposite direction of the current. See, this is the direction of the current and you are moving in the opposite direction of current. You have to take this sign time the positive sign. Positive sign you have to take. Okay. And this is I minus I1. First you have to write the value of the current and multiply it with the resistance that we have. That is R3 resistance we have, and this is equal to 0. According to KVL, summation of all the voltages in a loop is equal to 0. Okay. We already know this Ig is equal to 0. There will be no current in the galvanometer. Okay. There will be no current in the galvanometer. No current in the galvanometer. So put Ig is equal to 0. When you will put Ig is equal to 0, then you will get in this equation. Suppose this is the equation 1, you will put Ig is equal to 0. In equation 1 you will put. So this will become I1 into R1. Okay. And this Ig is 0. And this 0 multiplied by Z will become 0. Okay. So this whole term will become 0. So now we have this plus I minus I1 into R3 is equal to 0. Now further we will solve it. This is I1 into R1. This is equal to minus I1 into R3. This minus and minus will be cancelled out. This minus and minus will be cancelled out. You can write this as I1 divided by I minus I1. Okay. You will take this current I minus I1 in the denominator, and you will take this R1 in the denominator here. Here R3 by R1. So this is our equation number 2. This is our equation number 2. And we get this equation by applying the KVL in this loop A, B, D, A. Now I am choosing a loop B, C, D, B. B, C, D, B. Okay. I am choosing a loop B, C, D, B. Now focus on the loop B, C, D, B. Okay. Now apply KVL on BC DB. So from B to C, when you are moving from B to C, you are moving in the direction of the current. So you will take this I minus Ig into R2 positive, sorry, negative, minus I minus Ig okay, sorry, this is I1, okay, because this is I1 and this is also I1, okay, so this is I1 and this is I1, okay. So you will write here I1 minus Ig into R2, okay, and when you will apply it from C to D, when you will move from C to D, then you will write, you are moving in the opposite direction of the current, so you will take positive sign of the voltage, you will write I minus I1 plus Ig into R4. See here, you are moving from C to D, okay, you are moving in the opposite direction of current, that is why I have taken here the positive sign, and you will multiply this current with resistance, you will get the potential difference. So now you will move from D to A. When you will move from D to A, then you will again take the positive sign and you will write Ig into G. Ig into G, this is equal to 0, okay, and I am supposing this as equation number 3. So now put Ig is equal to 0 in equation 3. When you will, we already know the current in the galvanometer is 0, okay, because this condition will be only fulfilled R1 divided by R2 equal to R3 divided by R4. Now put Ig is equal to 0. Now you will put Ig here equal to 0 and Ig here equal to 0 and Ig here equal to 0. When you will put this, you will get minus, this is I1 minus 0 into R2 plus here you will get I minus I1 plus 0 into R4, and this Ig you will put 0 into G equal to 0. Now further when you will solve it, you will get it as minus I1 into R2 plus I minus I1 into R4, I minus I1 into R4 equal to 0. Okay. Now further, this is I1 into R2, this is equal to minus I minus I1 into R4, okay, and this minus and minus will be cancel out, okay. Now you can take this I minus I1 in the denominator of I1, so this is I1 and this is I minus I1 and this is equal to R4 divided by R2, okay, and suppose this is the equation number 4. So now you can see equation number 2 and equation number 4. When you will compare equation number 2 and equation number 4, see here in equation number 2, I divided by I1 minus I2 is equal to this, and again the same quantity I1 divided by I minus I1 is equal to R4 divided by R2. So you will write R3 by R1 when you will compare equation 3, equation 2 and 4, sorry. When you will compare equation 2 and 4, you will get R3 by R1 is equal to R4 divided by R2. Okay. So now what you can do, you can just replace this R1 can go here and this R4 can come here. Okay. So you can write this R3 by R4 is equal to R1 divided by R2. So if you want to write it like this, R1 divided by R2 is equal to R3 divided by R4, hence proved. Okay, this condition is proved. Nida and Hamza, are you getting this? Means Hamza, have you got this?
Yes, sir.
I have just applied the Kirchhoff voltage law. If you know the Kirchhoff voltage law, if you know how to apply the Kirchhoff voltage law, okay, okay, fine. If you know how to apply the Kirchhoff's voltage law, then there is nothing complicated to prove this thing. Okay, all of you If you want to note it down, then please you can. And Nida, and from the next to next class, we will start the moving charges and magnetism. Okay, from the next to next class, I think we will start the new chapter, moving charges and magnetism. So I think at that time you will be comfortable. Hamza, taken the screenshots?
1 minute, sir.
Okay.
Done.
And if you have any doubt, both of you, Nida and Hamza, and you can just ask me. Okay, very good. And you will get at least 2 or 3 marks for this type of question in your exam. Okay, Hamza, take the screenshot. Now this is finished. 95% of this chapter has been finished. 95, not 95, 98% is finished. 99% is finished. Taken the screenshot, Hamza? Okay, fine.
1 minute, sir.
Nida, are you taking the screenshots or you are writing on the paper?
Okay, sir. Done.
Okay, done. Okay, fine. Just take the screenshot of this. And please show the direction and don't make this diagram again and again, okay? If you are writing, then I'm fine. Take the screenshot of this. Our next topic will be meter bridge. Hamza, should I scroll down?
1 minute, sir. Let me take the screenshot. Done.
Okay. Just complete it. Then we will start meter bridge.
Okay, done.
Okay. So meter bridge basically is based on the Wheatstone bridge. Okay, is based on the Wheatstone bridge. Okay, completed this. Now we have, and a potentiometer is not the part of your syllabus. Okay, so I am leaving the potentiometer. We have meter bridge in our syllabus, so we will discuss meter bridge. So we will discuss first the what is meter bridge, and after that we will discuss the principle of meter bridge and construction and theory of meter bridge. Okay, this is very easy topic. Okay, so this meter bridge is basically the practical application of Wheatstone bridge. This is the practical application of Wheatstone bridge. First point is this, and what is the use of this meter bridge? This meter bridge is used to calculate the unknown resistance, and there is one experiment also in your syllabus. Okay, means in your lab, then you will go in your lab, you will do the experiment also. So there you will see the in actual what is the meter bridge. Okay, and here we are discussing the construction and all that. Okay. So second point is this is used to calculate the unknown resistance. Now, what is the principle of this meter bridge? So this principle of meter bridge means meter bridge is based on the principle of balancing of Wheatstone bridge. Okay. It is based on the principle of balancing of Wheatstone bridge. Wheatstone bridge. And what is the Wheatstone bridge? This is the Wheatstone bridge. See this now. This is the Wheatstone bridge. If what is the balancing condition and how the balancing condition will be followed? If you have R1 divided by R2 is equal to R3 divided by R4. Okay, and now here instead of R5, I am connecting a galvanometer. I am connecting a galvanometer of resistance G. Okay, so suppose the Ig is the current in the galvanometer. So if this condition is followed, Ig is equal to 0. So this is the principle of meter bridge. Okay. Okay, just leave that. So now construction of meter bridge means in exam they will ask you the construction of meter bridge. They may ask you the construction of meter bridge. So how you will construct that? So construction is very simple. Just see the construction. Now see here. These are the copper strips. These are the copper strips. Okay. These strips are made up of copper. And these strips are arranged like this. And what we have done, we have just connected a resistance here, and we have just connected a resistance here, and meter bridge is deleted. Are you sure?
Yes.
Okay, let me check it. I think potentiometer was deleted. I am showing you the syllabus. Then why we are wasting our time? You are right. And thank you. So see the syllabus, all of you. Okay, Hamza, you can rejoin. Okay, so this is the syllabus now, and deleted topics are uh, series and parallel combination. Meter bridge is also deleted. So no need to discuss this. Okay. Okay, fine. So just tell me a little bit about it. Okay, if you will give some other exam like any other competitive exam, then from there this is not deleted. So just let me finish this in 10 minutes. Okay. So Hamza, hello. Now your mic is okay.
Yes, sir.
Okay. This topic na is deleted from that your syllabus. Okay. So just you can skip it, and I am just telling, I am just completing it. Okay. I will take only 10 minutes because you can get this in the competitive exam. You will give. Then after that we will just finish this chapter. Hit by the with the help after discussion of heating effect of current. Okay. Because your knowledge will never be wasted. Okay. This is deleted from the syllabus. Okay. And if you will go for the higher studies and all that, then maybe you will get. No, who knows? Okay. So here a wire is connected. Don't think I am wasting the time. Uh, and here a galvanometer is connected and a jockey is connected. And suppose this is resistance R1, this is resistance R2, and suppose at this point there is no deflection in the galvanometer. So this is the length. Suppose at a length L, from this point, suppose this point is A, this point is B, okay, this point is C, and this point is D. Okay, and from here to here the length will be 100 minus L. Why 100 minus L? Because this 100 centimeter we will take. So just this wire has some resistance. We have already discussed that wires have the resistance because of the collision of electron due to the ions. Okay. So suppose guys, my voice is okay na? Nida and Hamza. Is my voice is okay? Means is my
Yes,
voice
sir.
breaking?
No.
Is okay, that's fine. Okay, so this is the wire na, from A to D is one wire, and you can imagine from D to C there is another wire. And suppose in this wire AD there is a resistance R3, and in this wire DC there is a resistance R4. And now I want to calculate R3. We have a formula of resistance. R is equal to rho L divided by A. Rho is the resistivity, L is the length of the wire, A is the area of cross section of the wire. So resistivity of the wire will not change because the material of the wire is same, and area of cross section of the wire will remain same. If we want to calculate R3, then we can write rho L divided by A. If we want to calculate R4, then I will write rho length this time will become 100 minus L divided by A. So if this is the neutral point, means there is no current in the galvanometer, Ig is equal to 0 at this point. So we can write R1 is equal to R2, R1 divided by R2 is equal to R3 divided by R4, and R1 divided by R2. What is R3? Rho L divided by A. This is rho 100 minus L divided by A. Now from here you can write this is A, this is rho, this is 100 minus L, this is cancel out, this rho cancel out, and you will get R1 by R2 L divided by 100 minus L. That's all for meter bridge. Okay. So if you do not know R1, then with the help of R2 and L, you can find R1. If you do not know R2, okay, then you can. If you want to copy this, then copy. Otherwise, you can leave it up. Leave this topic. No problem. Hamza, do you want to copy it or not? Okay, take the screenshot. It will help you. Means if you will
Yes, sir.
give, okay. Because knowledge will never. No, knowledge is never waste.
So you can scroll down. Done.
Okay, take this.
Done.
Okay, now. Okay, this is finished.
Done.
Okay, now this is finished. So means we do not have to solve these two numericals also. Okay, because this is not the part of our syllabus. So I am leaving these two numericals also. Now I am directly moving to the last topic of this. This is the last topic of this chapter, and after that this chapter will be finished. Heating effect of current. Heating effect of current. Okay. Fine. So now see now. What is the heating effect of current? This is the wire, okay, and in this wire the current will flow because this is a conducting wire, okay. So whenever in a wire current flows, heat will be generated due to the resistance of the wire. And what is the cause of the resistance? The cause of the resistance is in drift velocity. If you know the concept of the drift velocity, then you will know that electron collides with the ions present in the conductor. In conductor, there are millions of free electrons. There are millions of free electrons, and there are ions also. So when we applied the electric field, so what happens? Electron due to that electric field, there is a force on the electron, and due to the force, the acceleration is generated in the electron, and due to that acceleration, the electron got some velocity, and electron got some velocity means electron will move from one point to another, and in its path there will be the ion, and due to the collision of the ions, the current will decrease. Current will decrease. Okay, because what is current? Current is the flow of the charge only. Whenever the charge flows, there will be a current. Current is charge per unit time, charge flowing per unit time. So there is a property, you can say, of a wire or of a conductor, which opposes the flow of current, which opposes the flow of current, named as the resistance. And due to this resistance, whenever the current flows in the wire, heat is produced in the wire. And if someone is asking why the heat is producing in the wire, because due to the collision of large number of electrons with the ions, the heat will be produced. Okay, and this heating effect of current, this is known as the heating effect of current. So for the simplification, I am taking a circuit. Suppose we have this, suppose I have this circuit and current is flowing like this from here to here, and this is the resistance R. So see here, a cell is connected with a resistance R. Cell is connected with a resistance R. I have already told you, if the current I flow through this resistance, through this resistor. And one thing more I want to tell you, here I am taking this as an ideal wire, because due to this wire, when the current will flow in this wire, there will be no heat generation. Okay, I am taking this ideal wire. So as for the simplification, the heat will only generated in the resistance. Okay, in the resistance. So whenever the current flows through the resistor, there will be the heat generation. So you can write, when current flows, heat is generated across resistor. And now what is the cause of this? If you want to write the cause, due to the collision of, due to the collision of electrons, due to the collision of electrons and ions, heat is generated. Or you can say, you are supplying the energy from this cell. Na? Suppose E is the EMF of this cell, and you are the supplying energy from the cell to this resistance. And what is happening? In the form of heat, the energy is wasted. Okay, in the form of heat, the energy is wasted. You can check your laptop right now. In your laptop, definitely there will be some heating. This heating is happening due to the resistance of the wires in the laptop. Okay, so heat is generated, uh, or you can say, a part of electrical energy, a part of electrical energy dissipated as heat. You are supplying the electrical energy from here, here, and at this point, some energy is just converting into heat. So that heat is of no use. Okay, that heat is just a waste. Now, how you will calculate that heat? How much amount of heat is generated if I current is flowing and R is the resistance? Okay. So please remember this circuit. Suppose you have this circuit. This is the EMF E. And what is the potential difference across this? This is equal to V is equal to IR. Potential difference across this resistance is equal to IR. Okay. So now we will calculate power dissipated. First, we will discuss power, because we have formulas for calculating power, and with the help of power we can calculate energy. And power dissipated, I will symbolize it as capital P. So basically you can say power is equal to heat generated or heat energy produced divided by the time in which this heat energy is producing, divided by the time. Power is heat divided by time, you can simply say. And the formula of power, hmm, suppose you have this circuit, and formula of power is equal to I square R is equal to V square divided by R is equal to VI. This is the formula of power dissipated across resistance. Power dissipated across resistance R here. Okay. So I square R means current is I square R you can take, B square R you can take, and B and I simply you can take. This is the power dissipated. Now, if you want to calculate the heat energy dissipated or heat dissipated, this is represented by capital H. So what you will do, see here, if you want to calculate heat, then what you will do, heat is equal to power into time. You will multiply power with time. Power with time means, what is the formula of power? You will write this, I square R is the power into time, V square divided by R into time, Vi into time. So this is the heat dissipated. In this way you can calculate the heat dissipated in the circuit. Okay. And this is finished now. But I note, there is one note. If the power is variable, means power dissipation is changing with respect to time. Suppose at time t1 the power dissipated is 8 watt, at time t2 the power dissipated, means with respect to time there is a change in the power dissipation. If you can say, if power is variable, then you will, if power is variable and you want to calculate the heat energy, then you will write it like power into dt. Okay. P is the variable power, dt is the small amount of time. You will do the integration. Okay. And now if you will talk about the SI unit of power, Nida, do you know what is the SI unit of power? If you don't want to speak, then you can write in the chat box. Very good. Watt. The SI unit of power is watt, or sometimes power is equal to heat divided by time. So the unit of heat is joule and the unit of time is joule per second. So you can write this as joule per second also. Joule per second. Watt or joule per second is same thing. And one thing I want to write here, there is one thing, 1 kilowatt hour. 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joule. If your power dissipation is this, then it means this amount of energy is dissipating. Okay, now I am taking a numerical, and after this is the last numerical of this chapter, and this is a good numerical, I will say. Now, see here, first, if you want to solve the numerical, the first and the foremost thing is to read the question properly. Just read the question properly. They are saying two wires of same mass having the ratio of length this, density this, resistivity this are connected one by one to the same voltage supply. Okay. The rate of heat dissipation in the first wire is 10 watt. Find the rate of heat dissipation in the second wire. So suppose you have this wire. Okay. Suppose you have this wire and you have connected this wire with some voltage. Okay, with some voltage. Suppose you have connected this with the voltage V. Okay, and suppose L1 is the length of this wire. Okay, and ρ1 is the resistivity of this wire, and for the density, what should I use? Density, I will use this. Suppose I am supposing sigma as the density, not sigma. Okay, sigma you can suppose the density of the wire, sigma 1. So I am telling you the meaning of the symbols. Rho is the resistivity, and sigma is the density. Sigma is the symbol of density. So this is the first wire we have, and now we have another second wire. We have another second wire. This is the second wire, and we have connected this second wire with the same voltage supply. Same voltage supply we have connected, and this has the length L2. And one thing more I want to tell you here. Suppose A1 is the area of cross section of this wire and A2 is the area of cross section of this wire. Okay. A1 is the area of cross section of this first wire and A2 is the area of cross section of this second wire. And suppose the resistivity and the density of this wire is this sigma 2. Now they are saying the rate of heat dissipation in the first wire, rate of heat dissipation. See this word, rate of heat dissipation means heat divided by time. If the rate is involved, then time involved in the denominator. Okay, time is involved in the denominator. Rate of heat dissipation means heat dissipated per unit time, and this is known as the power. So it means indirectly they are saying the power dissipated in the first wire is 10 watt. So I am writing here P1 is 10 watt, and we have to calculate P2. We have to calculate P2. Okay. So what I am doing, I am just writing the formula of P1. We have three formulas of P1. I square R, V square divided by or Vi. I am just applying this formula. And why I am applying this formula? V1 is square divided by R1. And here I am applying P2. V2 square divided by R2, and P1 is V square by R1, and P2 is equal to V square by R2. Why I have applied this formula? Because I know that the voltage is same. I know that voltage across both the wire will same. So when we will take the ratio, these will cancel it out. So P1 by P2 if you will take, then V square by R1 divided by V square by R2. So P1 by P2 you will get, P1 by P2 you will get, this V square will cancel out, then you will get R2 divided by R1. This is equation 1. Now you have to just calculate the ratio of resistance of this wire and the resistance of this wire. You will get the answer. And now tell me, what is the formula of the resistance? R is equal to rho L divided by A. For the wire, the resistance is given by rho L divided by A. So for the wire 1, resistance, suppose R1 if you want to calculate, so you will write rho 1 L1 divided by A1. For wire R2, then you will write rho 2 L2 divided by A2. So if you want to calculate ratio of R1 divided by R2, then you will write rho 1 L1 divided by A1 divided by rho 2 L2 divided by A2. Okay, now this is the simple calculation you can do. Rho 1 L1 divided by A1. Now this A1 will be here, this will be rho 2 into L2. Okay, now R1 divided by R2. Now I will rearrange this. We have rho 2 divided, sorry, this is rho 1, this is rho 1. Okay, now see here, this is rho 1 divided by rho 2. I can write here rho 1 divided by rho 2 I can write. Okay, and I can also write this, this is A2 here, this is A2 here. I can also write this as L1 divided by L2. Just focus on this equation. Rho 1 divided by rho 2, L1 divided by L2, and A2 divided by A1. A2 divided by A1. Rho 1 divided by rho 2, this is. And in the question it is given that ratio of length, mean L1 by L2 is given. L1 by L2 is given as 1:2, means 1 divided by 2 is given. Okay, 1 divided by this is given, and rho 1 and what is given? Density also given. Density also given, and resistivity is given as 2:1. So rho 1 divided by rho 2 is equal to 2 divided by 1. This is also given. Okay. One thing also given, sigma 1 divided by sigma 2, means the density of both, the ratio of density of both the wire is given as 1:3. 1 divided by 3 means 1 divided by 3. Now put L1 by L2 here, put L1 by L2 here, rho 1 by rho 2 here, and but we do not have this quantity A2 by A1. So what we will do? So for this A2 by A1, for this A2 by A1, we will use the volume. For the volume, if you want to calculate volume of any cylindrical wire, then you will write area into length, area into length. Okay, and if you want to calculate the mass m of any wire, mass, what is the mass? Mass is volume into density. Suppose the mass m1 of the wire is volume of wire, means A1 into L1. A1 into L1 is the volume of the wire and density of the wire. And M2 is the mass of the wire. This will become A2, L2 and sigma 2. Okay. A2, L2 and sigma 2. But how we will solve this now? Here it is given that same mass. Everything is given in the question. The mass is same. So we will put this is equal to this. M1 is equal to M2 we will put. So what is M1? A1 L1 sigma 1 is equal to A2 L2 sigma 2. Okay. So we have A1 divided by A2 and we have L1 divided by L2, and here it will be sigma 2 by sigma 1. Now what is A? Oh, just a minute. We have to calculate actually A1 by A2 now. We have to calculate A1 by A2. So we can write this as A1 and this A2 will be in the denominator. Here we can write L2 divided by L1 multiplied by sigma 2 divided by sigma 1. So this is A1 divided by A2, and now ratio of L1 by L2 is 1:2. So what is L2 by L1? L2 by L1 is equal to 2 by 1. L2 by L1 is equal to 2 divided by 1. Okay. Sigma 2 by sigma 1 we have to find. Sigma 1 and sigma 2 is given. Sigma 1 divided by sigma 2 is given, and we have to find sigma 2 divided by sigma 1. This will become 3 divided by 1. This will become 3 divided by 1, and this when you will multiply you will get 6 divided by 1. So A1 by A2 is 6 divided by 1. So now this is the equation you have. This is the equation you have. R1 divided by R means this is P2 divided by P1. This is not okay. P2 divided by P1. So you can see here. Okay. Okay. Just don't do it now. We will do it afterwards. Otherwise, you will get confused. So R1 by R2. We have now rho 1 by rho 2. Rho 1 by rho 1 by rho 2 is 2 by 1. Okay. This is 2 by 1 we have. L1 by L2. What is L1 by L2? L1 by L2 is equal to 1 divided by 2. So this is 1 divided by 2. Now we have A2 by A1. A2 by A1 is 6 by 1. This is 6 by 1. So you will get this 2 and 2 cancel out. You will get 6 divided by 1. And what is the equation? What is the relation between the resistance and the power we have? So this is the equation number 1. This is power in the one wire is given. Power dissipation in one wire is given as 10 watt. So put the value of P1 as 10 watt. We have to find P2. Now we have R2 by R1. Means R1 by R2 we have 6 by 1. So we can calculate R2 by R1 from here. This will become 1 divided by 6. You will reciprocal of this. Okay. This will become reciprocal of this 1 by 6. So this is 1 divided by 6. When you will calculate P2, you will cross multiply 10 into 6. So P2 you will get 60 watt. So this is a very good question. Okay. Just please all of you note it down. I have tried to solve this question the simplest possible way. Okay. Nida and Hamza, just please note it down. So this is the end of this chapter. From the next class, I will start moving charges and magnetism. Nida, are you writing? Okay, already noted whole question. Means whole answer. Just wait. You have completed till here. Very good. Your writing is very fast. Okay, fine. And do you want to ask any doubt in this question? Means,
No, sir.
okay, means everything is clear. You have to simply apply the formulas and put the values. And definitely, if you will do this thing correctly, you will get your answer correct and you will get full marks. Okay, so this is the end of this chapter, and inshallah we will meet. If we will have a class, then we will meet in the next class, and I will start the moving charges and magnitudes.